Starting today.
Starting today.
Now.
Yeah. So we nice film like today. Doron has been at the IIS where he was a Chandra fellow. Before that, I guess you got your PhD with a guy in Netzer?
Yeah, Tel Aviv University. Right.
Yeah, he works on lots of things, including AGN. So he was telling us about the universe through the slit.
Okay, so the talk will be a bit eclectic, encompassing all sorts of things, but basically my aim is to try to show or persuade you that there is use for spectroscopy in terms of relating to some specific problems in astrophysics and how the spectroscopy can be used to give us some hint on what is going on. Specifically, I'll discuss 4 problems. One relates to the opacity of the universe, specifically that of galaxy clusters. The other one is dark matter detection, where I'll try to convince you that it is possible, although we don't know, maybe to detect dark matter through its spectroscopic signatures in some compact objects. Something to do with the missing baryon problem in relation to the halos, extended halos of galaxies. And lastly, if I make it, quasar structure and feedback. If I get through the first 2, I'll be very happy. I don't know about the rest. We'll see how it goes. Okay, so first, the opacity of the universe. So Zwicky, yeah, that's from Google, decided to count the number of galaxies, the galaxy density behind the cluster, behind the centers of the cluster, and compare it to the galaxy density of background galaxies, that is, background to the cluster, far from the center. And he found that the density of galaxies toward the center of the cluster was lower than that in the field. So he deduced that galaxy clusters contain dust. He said it is dust, it extincts the light from background objects, and therefore you don't see it in a magnitude-limited sample. So that was the opening of a crusade, so to say, to find the properties of the dust in galaxy clusters. And there were all kinds of papers dating back to Zwicky's work, and then 69 Karash and Tsev found that the optical depth, let's say, or extinction in the R band or B band is of order of 0.1, 0.2 magnitudes. And they speculated that this is dust in the clusters of galaxies. Then Brian Boyle did the same thing with quasars instead of galaxies, quasars behind the cluster, and tried to estimate how much dust you have there in clusters of galaxies, nearby clusters, and he found more or less the same answer. Later on, Roger Romani and Dan Maoz again looked behind the Bell clusters to count the objects, and they found that they have a deficit of around 25%, and this deficit could be explained by the presence of dust in galaxy clusters. Later on, a few years later, Dan Maoz, the same author on the previous paper, tried to figure out what the reddening is by comparing quasar colors behind the clusters to those in the field. And he found no reddening, basically down to a limit of 0.05 magnitudes. And his later conclusion was that whatever they were missing in terms of number counts of objects was primarily due to selection effects rather than real dust. I don't remember whether he discussed gray dust in his paper, but essentially ISM-like dust wasn't there to some limit. Esther Hu looked at Lyman alpha emission and dust properties in clusters of galaxies with cooling flows. This is a subset of clusters of galaxies, and she did find EB minus V of order 0.2 magnitudes. Later on, similar authors, some authors did another color experiment with clusters. They couldn't find any reddening down to some limit. Dust has been also looked in emission to see in the infrared, far infrared, to see the signatures of dust emission. But then it's always a problem because you don't know whether you're seeing galaxies, unresolved galaxies, in terms of infrared emission, or dust in the galaxies, or whether it's some diffuse component. So you cannot really tell. Stickel found some estimate for the mass dust of order 10 to the 7 solar masses based on the colors that they find and the distribution. But then their findings were actually probably ruled out by another group who did another study and concluded that Sirius emission in front of the cluster, was a major problem. In our galaxy, was a major problem for the analysis of the observations. So, as you can see, we don't know whether intercluster dust exists on large scales. We know that individual galaxies in a cluster do contain dust, but we don't know whether it's diffused also. We don't know what the distribution is, whether it follows the galaxies, whether it's compact, whether it's clumpy, and we have no idea what the dependence on the cluster properties is. So what we did is we tried to tackle this problem by using SDSS, and the SDSS has now around 10 to the 4 galaxy clusters selected simply by their grouping on the sky and in redshift space. And Kester et al. Did a major work on that, and they identified all the clusters with a mean redshift of 0.2. And the velocity dispersion that we are looking into is very rich clusters, the velocity dispersion above 400 kilometers per second, and simply because the properties of the sample are relatively well known. Below that, we don't really understand the selection effects going into the analysis. And we also use the DR5 spectroscopic catalog of quasars. We have quasar colors, we have quasar spectra. These are confirmed quasars. These are not stars or some contaminants of those. And we have all the photometric and spectroscopic properties. And what we did was simply correlate the cluster catalog and the quasar catalog in the way that we have a quasar behind the cluster, and we have its redshift, we have its photometric properties, and we have the spectrum. And then we compare it to a quasar in the field, far away from the cluster center, with more or less the same redshift up to some tolerance. And we can simply see what the spectral ratio is. So what do we expect to have? In principle, the cluster could boost up the flux by lensing, okay? And this is an achromatic effect. If you have reddening, if you have dust, it will redden the spectrum, and therefore you have this the spectral ratio going down because you extinct the red parts of the spectrum. In principle, you could also have gray dust, which is a bit problematic to identify because, again, it's supposed to be achromatic. These are large grains. But I'll discuss it later. We don't find any evidence for that. So these are the things that you can expect. One is lensing. The other one is reddening, which brings this down a bit.
Lensing can go both ways.
Sorry?
Lensing can also deplete your counts.
Yes. OK. So what we have, we are simply trying to understand what is the spectral ratio of quasars, not the number counts. We're not dealing with number counts here. Just want to see the reddening, not the extinction. If you have gray opacity, we won't be seeing that. OK, so what we did, we summed it over all the quasars and the clusters that we have, bringing all of them together to some common scale based on their R200, which is the radius within which the density of galaxies is 200 times that of the field. So everything is normalized. So we know we are dealing more or less about the same distances for all clusters or all sizes. And what we find is we find the following. So if you concentrate on this part of the diagram, this is roughly between 1.5 megaparsecs and 3 megaparsecs from the cluster center, okay, some annulus around the cluster. And what we see is we see signatures of reddening. That is, this part is higher than this part over here, which is the blue part of the spectrum. We can also see that the spectral ratio altogether is above unity. So what we think we see here is, first of all, the effects of gravitational lensing, okay, which simply boosts up the flux because it's higher than unity compared to the rest of the population. I'll get back to it a bit later. And then you see also a tilt here because of the reddening. Okay? So this is what we have for between 1.5 and 3 megaparsec scales. A few thousand, roughly 2,000 objects. Okay, so this is carbon-4. So it seems like it is an absorption, but this is a special effect that we think is the following. In a magnitude-limited sample, when you have gravitational lensing, you're seeing a fainter part of the population, which generally would not be so unless you had this boost by gravitational lensing. And we know that there is a Baldwin effect where the emission lines of the quasars depend somewhat on the luminosity. So what we think we see here is we see signatures of this Baldwin effect, and it's roughly the same magnitude and sign that we expect. Here you also have reddening, but you have somewhat lower ratio, presumably because gravitational lensing is less important. We are going to larger scales, between 3 and 6 megaparsecs.
So you think the ratio of quasars that are either in the cluster or not in the cluster?
Yes, we're looking at colors. Yes, spectral ratio.
Behind the cluster, not behind the
But
cluster.
it's the same redshift.
Yes, these are the same redshift.
That's the same redshift, but it's a different quasar. So
Yes.
and then the increase of 2% in flux is just saying you're trying to say that the pulsar behind the cluster is an average 2% wider than a quasar which is not behind the cluster.
That's our interpretation. Okay, but you have many, many things here related also to the population of the quasars. Okay,
Well,
yes.
but if you look at Quantum and Narkin Company, and what they showed very convincingly is that when you have lensing of quasars, then depending on how wide a quasar you choose, the lens quasars can get fainter.
Okay.
Because you're below the depletion regime and not in the magnification regime.
Okay, we take this fact into account a bit later. I'll discuss this point, okay? I'll discuss it a bit further. And what we have here, when we go to larger scales, we more or less get to zero reddening and very low or no magnification of the objects. So overall, the trains are sensible, make sense, okay?
Please tell us again, what is R200? How do you
R200 is defined as the radius within which, in the cluster, within which the density of galaxies is 200 times that of the field. This is R200. Different clusters have different R200s. They have different masses.
What is this compared to the very great cluster typically?
So it's of order unity, factor of order unity. It's supposed to be the same, but it depends on how you define it. Okay, so it's all matter of definition. The real radius is some vague definition, depends. Some authors take it to 100 times, some authors take it to 200. Depends. That's of order unity. And in physical size, this is around 1 megaparsec.
So is it fair to say that you are looking at a dimer and dimer population as you get closer?
If you think the gravitational lensing is in effect, yes, then in a magnitude limited sample, you see to fainter part of the luminosity function of the object.
So is it possible that dimer quasars have more dust intrinsically rather than dust being reflected?
Okay, so it could be many, many things, but let me just get to the following slide, which may be of some interest. Okay, so this is the results of the photometric. I'm talking about the left side here. This is the results of the spectroscopic analysis when we sum up over all the objects and make the means, all the statistics. And what we find is that the EG minus I, again, we chose these SDSS colors, reddening, so to say, is of order a few times 10 to the minus 2, and then it decreases. There is some kind of a core here, seems to be a core, and then it decreases with the slope of minus 1, roughly. Okay? And this is this slope is what you expect, let's say, if you have a distribution of a singular isothermal sphere, or densities that goes down as r to the minus 2. Okay? When you get to the column density or to the reddening, you get the slope of a minus 1. So this is what we find for the clusters. And if we try to estimate the mass that we have in dust, if everything is constrained within this 2 megaparsec scales, at least for the first bin, then we get something like 10 to the 9 solar masses of dust. Now, if we take the results of the lensing, or what we interpret as lensing, that is how much is the flux boosted, then we get something of this this graph where the slope is minus 1 over the entire radius range. Okay, this, yes, okay, so this is after correcting for the reddening. Okay, we have a spectrum. First of all, it's boosted up, and then it's tilted by reddening. And what we did is, given the ratio that we find for the reddening, we correct for it, and then we measure what is the flux ratio compared to unity that we have.
SMC extinction.
Yes. I use an SMC extinction curve, but it doesn't depend much, even if I use a galaxy in this wavelength range. Of course, it can be many, many things. It's consistent with SMC. Okay, so what we find, this is interesting. So for the dust, we find a core. For the lensing, we do not find a core. And this seems to suggest to me that if you're talking about things, let's say, like this effect that you have where fainter quasars are actually dustier for some reason, then I would have expected if these two to have the same trend. Because you're seeing even a fainter part of the quasar population, which presumably would be even more dusty, and then you would expect this to go up as well. But no, you have a core here. So this seems to suggest that maybe we have something which is real. I mean, the problem with this field that it's plagued with studies that claim that you have dust, you don't have dust, you have dust, you don't have dust. What you need is you need another survey with another, let's say, selection effects to say exactly, well, to corroborate these results. But as far as we could tell, things look pretty, they make sense. We've done all kinds of checks. I'll get to those in a minute. And it seems to be rather robust. As far as what happens when you're seeing the effects of lensing in a population with a luminosity function, then in a magnitude limited sample, the mean magnitude of flux that you actually observe does not depend just on the effects of lensing, on the magnification. It depends also on the shape of the luminosity function. So what we did was simply take the luminosity function for quasars as we think it is, and take the selection function for the SDSS in a simplified manner but quite realistic, and account for this effect of magnitude of gravitational lensing and try to estimate what is the intrinsic lensing signal that we have, including the effect of luminosity function inside. And what we get is that instead of this 8% of lensing in the core of the cluster, at 1 megaparsec, let's say, the actual ratio should be around 3 times higher. So that is around 0.24. And this more or less agrees with simple models for singular isothermal sphere. If you take a cluster with some constant velocity dispersion.
So galaxy-galaxy lensing, for the same sample, you know exactly what the lensing is, right?
From
Galaxy-galaxy lensing by these clusters.
Okay, we haven't.
The same clusters, right?
Okay, we haven't done this analysis.
Also, Ben has done this analysis, right?
Ben Kester, in his paper, I'm not sure he did this analysis. I mean, there are yes, in his paper.
Also, papers by like Sheldon.
Because what they did, he identified the galaxies in the cluster, and you're talking about lensing behind the cluster.
I'm talking about the average mass profile of the
Okay.
cluster
Yeah.
as measured by stacking lensing signals of atmosphere.
Okay.
As measured, for these same clusters.
Mm-hmm.
And so you know exactly what the lensing is, right? And so I don't really see why you're doing this.
No, I'm just saying that you can derive this out of this. I'm not claiming here to have a new result about the lensing. What I'm claiming here is that it seems that our dust measurements in terms of reddening are pretty robust. I mean, they agree with several independent checks. I'm not claiming that the lensing is something new. Okay? It's just a corroboration that this makes sense, and the fact that you have a core here and not a core here makes sense.
And so the core you're, finding, that's in 2 dimensions, right?
Yes.
There's some projection.
Yes.
And you're seeing it flatten out at around like the real radius.
Yes.
So if there were no dust at all in 3D and
Right.
the real radius, you would also see
Right.
the same thing.
Exactly. Okay. So this is an interpretation. So what we think is going on is exactly what you said, is that the centers of clusters are relatively devoid of dust compared to the outskirts of the clusters. I mean,
The whole cluster is what you're saying, right? I mean,
well, it depends. Well, it depends how the dust is distributed. Okay. So if you have a constant density, if it doesn't rise up toward the cluster, then you will have just a constant density dust over all the entire universe. But it seems that the dust does follow matter in some sense. So you grow up. We wouldn't have seen a signal at all if it were just uniformly distributed dust over the entire universe.
right, so it's correlated with the clusters.
So it's correlated with the cluster outskirts, and the insides are probably devoid of dust with this interpretation. Okay? Yeah, you're right. And this,
If you believe that, what's the metallicity
the metallicity of
correspond?
the, it's much, so if you compare it to the ISM, so it's around, I think it's around 5% of the dust to gas that you expect for the ISM in our galaxy. Okay? So, so the main result is this one.
So that's again consistent with SMC type?
Yes, everything is consistent with MSMC, but it can also be galaxy. I mean, we don't see the bump. We have.
No, I mean, if you have much less dust, that means less metals than in the galaxy. So, and the SMC has about, what is it, 1/10?
Yeah. In this sense, yes, it's consistent with the MSMC, but you couldn't derive really say,
No,
aha.
I know. I'm just saying, sort of conceptually, if
Conceptually.
you want to think of it as lots of torn out SMCs there. That's
Yeah.
one way of thinking of it.
Yeah, I mean, you can find many consistencies there, but whether this is the, yeah, but you're right. Yeah, that's a general picture.
So you're saying your black line on the right side is equal to the lower line multiplied by deep side EM? No?
Yeah, when you do this and take into account the selection function of the SDSS, then it's roughly 3 times higher than what we actually measure that's supposed to be. So it's roughly here.
But that sounds like you're actually measuring the range where this changes sign, right? We think the question is because we've done that at the higher luminosity end, the magnification bias is strong and positive, and of order unity. I mean, this thing is exponential. And then as you go to the faint end, it goes negative. So it kind of looks like you're actually mixing positive and negative magnification to get this stuff suppression by factor of 3. So if you plot this now as a function of deep side EM, so it just takes the luminosity of every quasar and divided by deep side EM, then we should scale that all out and get a magnification weighted radius, which would test whether it really was lensing or not. I mean, that's a testable statement, right?
Yes, okay, I'll be interested to talk to you later about this test you just suggested. We haven't done this. We actually, our main goal was this thing over here, the reddening, not the lensing, and this was just some kind of a hint that we may be on the right track. But I'll be interested to talk to you later about this. Okay, so is it robust? Well, another thing that you have, and I haven't mentioned, is foreground cluster emission. You have the intracluster light, and you have galaxy members in the cluster, and they have some spectrum. And when you have these guys in the field, and you have a background quasar, what you're actually measuring in the PSF or the spectrum could be a combined effect. So it turns out that this effect could be important only if quasars pass closer than 10 kpc from a cluster member. And this happens only for less than 0.1% of the cases. So this doesn't explain the signal that we find. Plus, we made another check. We repeated the entire analysis by taking out all quasars closer than 30 kpc from individual cluster members, and we got the same result. So it's not foreground emission by the clusters. Luminosity-dependent quasar colors. It is possible, we don't know, that fainter quasars could actually be, let's say, bluer redder than more luminous quasars. So it's as if you have the effect of dust, but what you're actually seeing is you're seeing the intrinsic luminosity, the spectral energy distribution of the quasars vary. With the signal to noise that we have so far, it's difficult to check this effect, and the literatures don't give you a really robust test whether this effect is real or not, or whether you have it, because usually these things are color selected, and they have all kinds of selection effects, and you cannot tell what's going on, but this is something to bear in mind. Again, if the fact that we see a core in the reddening and not a core in the lensing signal, or the flux, let's say, whatever you interpret it, suggests that this thing is not very important, because otherwise you would expect both of them to follow the same trend, but they don't. So it seems to be relatively okay in this case. SDSN calibration issues, Brice is working on that a bit. I mean, at such levels, it's very difficult to say what's going on. The SDSS has been selected, had been tested for many, many things, but one has to test it more in this kind of small values of the magnification. But what we did do is that we have done the photometric and spectroscopic analysis independently, and we get consistent results for both of them. And both these data sets are relatively independent when it comes to all kinds of biases and selection effects. So is it robust? I would say it's interesting. I would say it's worth pursuing. I would say that so far it seems to be consistent with everything else we know. But again, this field is plagued with all kinds of things. This is the first time I think we we have the entire selection function of clusters now, and we test only mean quantities. So I would say it's relatively robust as far as observations in astrophysics are robust in many cases. Okay, so some things that come out of this analysis. You could just take all the clusters in the universe, assume that they do not evolve with time at all, no evolution, and you can simply calculate the reddening that you get up to some arbitrary high z, just by what you have that we find for redshift 0.2 clusters. So you have the cross-section, you have the mean reddening, and you simply integrate up to infinity. And what you see is you see this curve over here, which is below the supernovae from Rees et al. 1998, supernovae limits on the systematic reddening that you can have in their sample. So what we find here for the clusters is below, not by much, but somewhat below what Rees et al. 1988 find for the systematic reddening, not the extinction. The extinction is way up here, okay? So this is okay in terms of the cosmological constant and whatever limits they had in Rees et al. Another thing that you could try to see is what is the origin of this dust? Presumably dust comes from stars, comes from galaxies. We have galaxies in the cluster. So one possible model to explore is that you have galaxies. These are the galaxies, these faint dots here, and each of them simply ejects dust over cosmic time. And so these envelopes gradually evolve, expand until they overlap, and what we see, let's say, in redshift 0.2z, the redshift 0.2, is what we find in observations. So this very simple model we try to see is dust ejected by from galaxies by winds at some constant velocity. Galaxies at the core are not counted because dust is presumably sputtered very, very efficiently. They're on timescales much shorter than the Hubble time or the dynamical timescale of the envelope. So this is just a prescription that we used, very, very simple. You have some dust ejection yield, and this is the star formation rate. We assume proportionality between the dust ejected and the star formation rate. And these are both dependent on z in principle on the redshift. And you can have many ways. One of them is that galaxies eject constant mass loss rate of dust with time. Another possibility is that you have a very sharp peak where galaxies at a redshift of, let's say, 0.3, 0.4, whatever you have here, eject most of the dust out. So it's kind of a shell rather than a wind that gradually expands. So this is just to show you two very extreme scenarios. And then what you get, if you look at a galaxy, at a single galaxy, which is located here, and this is the distance from the galaxy in megaparsecs. Okay, this is 1 megaparsec. So this is what the envelope would look like if galaxies eject dust over cosmic time at a constant rate. It goes up to 1 megaparsec scales, let's say. Okay, gradually expanding over cosmic time. And the green line corresponds to this Gaussian here, where you have a very sharp emission of dust, ejection of dust, which produces somewhat of flat core here, and gradually you have a nebula. This part is simply flat because it's relatively devoid of dust, and you have just a shell expanding. And what we did is take this very simplified model and fit what we see for the clusters. We can simply fit it, and we get out the normalization of this model, and we get the galaxies should eject more than 10 to the 8 or around 10 to the 8 solar masses of dust from their cores. But if we say now that field galaxies are not much different than cluster galaxies, okay? Because we are talking not about galaxies in the center of the cluster. We're talking about galaxies 2-3 times the virial radius of a cluster. So we could say, okay, let's see if density doesn't matter much and it's the same evolution for the field galaxies. Then what we have in this case is that the total opacity, okay, this is exactly the same diagram you've seen before, just integrating the total reddening that we have up to arbitrary large z, then what we get is way beyond Rees et al. Results or constraints on the systematic reddening that you have. So what I'm saying here, I'm not saying we have a problem. What I'm saying here basically is this point here, this is a summary, but this point, there is an intimate link between cosmology and galaxy cluster formation with these results. So in principle, you could have pretty robust constraints on how galaxies in the clusters emit dust, eject dust. It could also tell you about galaxy evolution in general. So this is a really nice way to test these things, and this is one of the things we would like to do, also with BRIS, because BRIS is working on galaxy dust, not cluster dust. So this is a very nice thing to do, and what it could mean that the dust in clusters of galaxies behaves differently than what you expect from filled galaxies. Okay, so just to sum.
Yeah, again, I think, sorry for my naive pictures here, but one thing that clusters do very well is tear up galaxies probably near the center, and then it gets thrown out to large distances. So
yeah, so this is one possibility. This is one possibility. It would be some tidaling. I mean, actually, these interactions go like n squared, so in principle, you could have much more rapid. So this is one of the things we would like to understand better, what's going on.
that makes a prediction, because there should be then a corresponding number of stars also in this, dispersed stars in the
So you could,
halo
yeah,
at these distances.
yeah. So as far as, yeah. So there are some limits from intercluster light, from Zibetti.
That's far out?
Yeah, it goes far out.
Okay.
Yeah, and in principle, he took out all the resolved galaxies that he could see. So I don't know exactly what it tells you and how to compare it to the field, but in principle, you could do that. Okay. Switching gears a bit, dark matter, again, Zwicky. So Zwicky suggested that galaxy clusters are held together by dark matter. And what he did was very simple. He simply looked at the galaxies, measured their velocities, and then he said, okay, if you need it to be bound together, you must have more matter than you actually see. And this is the dark matter. And we have very good idea how it is distributed. Like this is, for example, from Broadhurst et al., and where they did strong lensing analysis. And this, they got splendid maps, and you can actually see the distribution around the cluster, whatever, and we know exactly that the 23% of the material is dark matter and the rest is dark energy and some stars. So we know all these wonderful things, but what we don't know is we don't know what is the physical nature of dark matter. What is the particle nature? How is it related to other physics? I mean, different theories have different predictions. You can have WIMPs, which are weakly interacting massive particles. You can have axions, all kinds of things, and this is related to supersymmetry and other things. And I won't be talking about WIMPs today because the name is not very nice. So I'll be talking about axions. So axions are one of the candidates for dark matter, and these are particles, very light particles, that although they are light, they are treated as cold dark matter because they come out of thermal equilibrium when the universe was formed, so they are cold dark matter. Their mass is around, presumably around 10 to the minus 5 eV, and their energy is 10 to the minus 9 kinetic energies. So there is one way to detect axions, and this is actually being done in several experiments around the world, is by the effect of light shining through walls. So these axions have a tiny interaction with the electromagnetic field. And in principle, an axion could turn into a photon, and a photon could turn into an axion. And what people do now in laboratories is they have a beam light, a laser, let's say, or something else, and they have a very strong magnet, and some fraction of the light will be converted, presumably converted into axions. And then they put a wall, a brick wall or something like that, and it blocks all the photons. Presumably axions can penetrate very easily because they don't interact with anything. They just move through the wall. And then you have another strong magnet which will convert a fraction of the axions back to photons. So that's the idea. And this idea goes back to Sikivi and Raffel and Stodolsky in 98. And now you have PVLAS and you have CAST. Both of them are ongoing experiment. PVLAS has recently, well, a few years ago, claimed to find the axion, but then it turned out that they have some systematic problems, so this result was discarded later. CAST got only upper limits on the mass and interaction, this coupling constant to the electromagnetic field. And this is still ongoing. They're now going to CAST 2, and this is in CERN. Basically, the probability to convert an axion to a photon or photon to axion goes as B squared times L squared. B is the strength of the magnetic field, and L is the size of the system. This is in the experiment, terrestrial experiment, this is 10 meters or something, a few meters. So you get some kind of number in some units, Gauss times centimeter square, you get 10 to the 16. But when you're talking about self-gravitating objects in astrophysics, you can get much, much higher numbers. For instance, for magnetars, you get numbers like 10 to the 42, many orders of magnitude above what you have in terrestrial experiments. And many other objects too. These are quasars, pulsars, magnetic stars, and these are X-ray binaries. So all of them, you get, in principle, higher conversion rates that you get on our planet Earth. So it could be useful to check those objects and see whether these can tell you something more about axions or these pseudoscalar particles that could be candidates for dark matter. So this is just a bit of formalism. I won't bore you too much with those details. But if you take a Lagrangian where you have the free electromagnetic field, this is the Lagrangian density of the free electromagnetic field, you take the free axion field and you introduce some interaction between the two, which would be a scalar. Again, the axion is pseudoscalar, this is a pseudoscalar, so everything is scalar. And you just solve the equations, including this source term, you get something like Maxwell equations, basically, with a source term. And this source term is the axion field for the electromagnetic field and the electromagnetic field for the axion field. Okay? And you do all the machinery, and in principle, you introduce two other things, which I haven't discussed here while solving for these expressions. And this is the fact that you have vacuum birefringence. That is, vacuum introduces some velocity dispersion. That is, photons with a given polarization will travel in a different velocity compared to photons with other polarization when you have a given magnetic field in the vacuum. Okay? And this thing is the effect of the plasma. Plasma also, of course, introduces. So what you do is all these terms which are very difficult to calculate, can actually be represented by this constant here. Okay, this is typically the velocity of the photons over c. This is what you get for ordinary materials like glass, like whatever, and this is how it enters into the expression here. And it includes unity, which is pure vacuum. It includes QED effects, which is this vacuum birefringence, and includes plasma effects. And you can also state it as if you have an effective dielectric constant of the plasma plus the vacuum. And these are the most important terms. So basically what you have when you're talking about plasma, you have a photon coming into a distribution of electrons and protons or electrons and positrons. And this thing will simply cause this movement of the electrons. And therefore, you have some coherent scattering, or basically this effect here where the phase velocity is a bit different in the material, in the plasma, plus the vacuum, compared to the pure vacuum without anything, without magnetic field. And so what you have is you have some effective dielectric constant, and it has some weird structure. Never mind that, but grossly what I'm talking about here is the fact that the dielectric constant goes down with frequency. This is frequencies, this is, let's say, optical frequencies, and this is X-ray frequencies. So it goes down with frequency like the plasma frequency to the -2. And you have this vacuum birefringence, which was calculated by Stephen Adler in '71. And this effectively dielectric constant simply grows with the magnetic field, first as the second power of the magnetic field, and then it flattens out. So these are the terms that are most important to actually say where the conversion occurs, okay? First of all, we have the probability for conversion, which seems to be very high, but then again, what we also need is we have to know where it happens on the energy scale of photons. And what determines that is exactly these two terms.
What is PC?
Sorry?
What is PC? Your critical magnetic field?
The critical magnetic field is around 4 times 10 to the 13 Gauss. And you get that in magnetars. You get to that in magnetars, but not in other objects, okay? Okay, so after a bit of algebra, what you get to actually compute these probabilities is you get a Schrödinger-like equation. And what's good about that is when you have a Schrödinger-like equation, you know how to calculate probabilities. That's the entire thing that is important for us. And this is a great help because otherwise it's very difficult. And what you have is if you have some initial state here, which could be, let's say, a photon, and then this photon propagates through vacuum with a magnetic field or plasma with a magnetic field, threaded by a magnetic field, it has a mixed state, which is a photon plus an axion. And then you make a measurement, let's say, at some point. And then you can know what the probability is simply by taking what you want. Let's say if you want an axion or you want a photon, and multiplying it in a scalar product with this mixed state, and square that, and you have the probability. This is how quantum mechanics goes. So when you actually do those calculations, you get that there is a resonance-like conversion there. There is a typical energy where the axion is very easily converted to a photon and vice versa. And this happens at some frequency of the photon, which physically translates to the fact that there is no effective momentum transfer to the field when you have this photon convert to an axion. So this is the frequency where you have no net momentum transmitted to the field. This is the frequency where you have the peak in the photon-axion conversion.
Is this the point that was singular on the plot of
No. So the point that was singular, So the points that were singular here are just the cyclotron frequencies. Cyclotron frequencies of the plasma. Here I took electron plasma and proton plasma, but you could have electron positron. Because if you had those at the cyclotron frequency, it will be a bit difficult to tell them apart because you have cyclotron lines and then you have some extra conversion feature from axions, and it will be difficult to tell them apart. So what we are looking for things that are not on the cyclotron frequencies. Now, in order to have this expression equals to 0, which is the momentum transfer, what you need is you must have plasma in the system. You cannot have resonance conversion of photons into axions and vice versa when you don't have plasma. And this is because if you need this to be 0, you need n to be smaller than 1, while both of these are greater than 0. This is 1, of course, and this is greater than 0. So you must have plasma in the system. Otherwise, you don't have resonance conversion. But you have plasma in astrophysics. There is no pure vacuum. Certainly, when it comes to very compact objects, they always have some plasma. So you need the presence of plasma. And there are a bit of issues when it comes to plasma physics that I haven't addressed yet. So the plot that you saw, which was very nice with all these resonances, is correct for very cold plasma. What you have in this case, and how you calculate it, you simply take a harmonic oscillator. That is, you take this electron, let's say, in a field of protons, and you hit it with a wave, with a photon wave, electric field, and then it simply bounces up and down, and then you can calculate the dielectric constant. But when it comes to hot plasma, the physics is a bit different, because with hot plasma, the electron can travel long distances over very short timescales. That is, it can travel over a wavelength over timescales which is comparable to the oscillation timescale. So what you have in this case is something of this sort. Oops. So it no longer traces exactly what you have in the waveform. And to include that thing, these effects into the calculation, this is very difficult. And I was fortunate enough to get in touch with some guys from Madrid, from CIEMAT, and who actually work in plasma physics laboratory, who were able to, and we're trying to calculate these things now. And hot plasma is usually what you have in very compact objects. For instance, magnetars and pulsars, these plasma is actually pair-producing. That is, what you have is you have a huge magnetic field rotating with very high velocities, and therefore you have an induced electric field, and this produces all the time pairs. And this is how you populate the magnetosphere of pulsars and magnetars with plasma. And this plasma is hot, it's not cold. So you have to take into account these effects too. This is just to show you what happens when you increase the temperature to some part of the dielectric tensor. This is just to show you that it's a non-negligible effect. It really kicks everything, it smears things considerably. And so if you want to know where your axion photon feature in the spectrum would be placed in optical, in X-rays, in gamma rays, you have to include these things too. So the rationale is simple. Now that we are done over with those calculations, what we want to do is very simple. We think we know more or less how objects emit radiation. And they emit radiation over broad spectral range. It could be, let's say, a black body radiation. It could be a parallel radiation. And if we can find a sharp feature due to axion photon conversion, like these things over here, then we may be able to attribute that to true physics rather than atomic features like lines that you have here. You have a broad Gaussian line, or you have an edge. Okay, so these things are very, very different in principle than what we'll have for the axion photon system. And this is what we're after. If you know more or less how your object emits, you can look for sharp features which are not atomic features and get the physics out of it. So spectral predictions for photon-particle oscillations, as far as we could tell, these are the first calculations that actually include most of the relevant physics to compact objects. And as you can see, well, it may be a bit difficult. This feature is very, very different from a Gaussian line. What you have is it's like a sinc function, inverted sinc function. So here's here it's in terms of velocity instead of wavelength. Okay, it doesn't really matter, and this is normalized flux. And what you have is a very, very broad feature, relatively broad feature in this case. It goes down and oscillates and goes up again. And the oscillation depends somewhat on the column density of plasma through which this photon propagates. Now, if you have varying magnetic field that varies with distance, then you can have a different feature, which is somewhat asymmetric, as you can see here. Still, you have these oscillations, but there is also some asymmetry. And in principle, you could calculate all these things for plausible scenarios for magnetars, for pulsars, things like that, and you can actually tell what's going on. You have specific predictions. So what we see is that these typical absorption features are very different from lines and edges, and this is good because you can tell them from the other features. And also, there are no counterparts in the spectrum, rather than unlike atomic lines. If you see, let's say, Lyman alpha in absorption, you may expect to see also Lyman beta in absorption. Certainly, the other way around. But here, you don't have any counterparts. So it's a single feature in the spectrum. Yes, I'm not saying these. The problem with these things is that it's not a controlled experiment. Right. Yeah. So it's always difficult to get those things. But given what we have now, I think it's worth the try.
What's the deepest that feature can be?
Oh, it depends very much. It could be. I mean, here it goes to practically zero flux. Okay, so it could be very deep. It very much depends on the distribution, on the column density that you have through which the photon propagates. It depends on how broad it is. I mean, because all...
variable coupling constant, I assume.
Yes, of course. Of course. And it depends, of course, on the resolution of the instrument you're working with. If your resolution is much poorer than 1,000 kilometers per second, it will never really reach... We're now working on making a grid of these spectral predictions. But what you can see already, that if you plot these diagrams where this is the axion mass and this is the coupling constant, then if you're talking about AGN, then this hatched region in red here is where you're sensitive to. And in principle, you could go down to coupling constants of, let's say, 10 to the minus 14. It doesn't mean you much. But what it does mean is that current terrestrial experiments like CAST, which is the best right now, is way up there. It's around 10 to the minus 10. So in principle, if you study AGN, you could go 4 orders of magnitude down in the coupling constant. if you're talking about pulsars now instead of AGN, then again, this is where current terrestrial experiments are. CUST, laser is even up high there. And this is what you have, what you probe with pulsars, 2 orders of magnitude roughly below what you have with CAST. There are also other experiments here, but they do not cover the full dynamic range in axion mass, and they cannot, for example, rule out an axion here. What these experiments do is that they essentially check for axions, which is a dark matter candidate. But if you don't have too many axions to begin with, that is, if axion is no dark matter but still exists, then these experiments won't be able to tell that. But the what we propose here with these astrophysical boundaries may be able to detect that.
So what is this blue band that looks so horribly below everything?
Yeah. So the axion models. This is what. So they have in the Lagrangian where this axion mass field was introduced. So you have a range of plausible models for the axion mass and coupling constant from QCD, which is roughly here, but it doesn't mean that it's just here. It's with high probability here, but it could be all over this diagram basically. We don't know where it is. Okay, so it's just, let's say, order of magnitude estimates that it's here based on the theory, but it could be everywhere. And PVLAS, by the way, the PVLAS experiment resulted in a point way up here. So this is where they said they've had this detection of axions, but then it went away. So,
So out of curiosity, why is there an upper limit on your pulsar?
Yeah, so the upper limit is essentially what happens is when you have too many oscillations in principle and you have low resolution instrument, it will simply be flat. You won't see any features. It will be like flat. So what we took here, we took resolution typical of the instruments we are working with, let's say in the X-rays. And we said, okay, this is what we can do, because if we have this resolution, it will just bring down the entire flux by some magnitude, like gray dust. But we won't be able to say, aha, this is a feature. So here we have it, here we don't. It's simply higher over there. Anyway, so the next step, first of all, is to make all these spectral predictions to conclude them, and then look in the archive. For HST, we have the Crab Nebula, which is an okay spectrum, not terribly good, and we intend to propose in the next cycle, with COS being the UV spectrometer up, we will attempt to propose for time on the Crab. And Chandra, you have a lot of X-ray binaries out there, and also AGN to try to see this feature. So this is what we were planning to do. So just a summary, photon-particle conversion induces unique features, as we saw. These are not lines, these are not edges, and they are very different from atomic ones, and this is good. The energy where such features are actually observed depends on many things, like the magnetic field strength, the density distribution in the compact objects. We don't have precise handle of those, but we do have estimates that, let's say, the density goes like the R⁻². The magnetic field is roughly a dipole in pulsars and magnetars. And if you use those things and you have good enough observation, in principle, you could get pretty robust constraints or even detection, which would be great on the axions. And this is currently not accessible by terrestrial experiments. So I won't have time, I guess, to go to the other part of the talk, which is about the missing baryon problem and something to do with quasar structure, but that's okay. I mean, I thought I'll get here. I wasn't sure whether I get to the rest of it. So I'm pleased. I hope you're too. Thanks. Yes.